Hi everyone. So this is a video on topics 4.6 and 4.7, local linearity and L'Hopital's rule. So 4.6 is local linearization and 4.7 is L'Hopital's rule. So we had a warm-up, Desmos exploration, estimates using tangent lines, check for understanding, and then some notes on L'Hopital's rule. The homework, we don't have new formatives, but the homework will be 4.6 and 4.7 with answer keys in the module. So for our warm-up, this is a graph I want you to look at in Desmos. It's the graph of a function in red, and then the tangent to that graph at the point 1, 2. And then I want you to zoom in on the point 1, 2 and think about what you notice about how the original function compares to its tangent line at x equals 1. So if you click on the link, that should give you the graph. And here's the point 1, 2, right? And so you're gonna zoom in on that point and think about what you noticed. You can pause the video now and zoom in on that point and think about what you noticed. Okay, so hopefully you've had a chance to pause the video and really look at it. So you notice, hopefully one of the things that you see is that the closer you zoom in on that point, the closer the tangent line actually approximates the graph. And that's what's meant by local linearity. The closer you zoom in on a function that's continuous and differentiable at a certain point, the closer it looks like, the more it looks like a line. It's not a line, but it gets closer and closer to the shape of a line. So the more you zoom in, the more it's not, the tangent line and the original graph are not really distinguishable from each other. So you see this picture right here, it's almost like you can't tell the difference between the graph, the blue graph and the red graph, okay? So what this means is that we can actually use the tangent line of a graph at a certain x value to estimate values of the function at that x value. It won't be the precise answer, but it's going to be close. And it really came in handy back, you know, before we had a lot of technology to do this without having to estimate. And we do want to kind of use it to estimate values of functions. Okay, so I'm going to do an example with you on paper of doing it like let's say we had to do it from a table. So I'm going to go ahead and share my document camera so you can see this example. Okay, so we're going to use this table. Okay, so the idea is that we can use tangent lines as an approximation for y values of a function. So let's say we have a function f of x, it's continuous and differentiable on the open interval from 1 to 4. Okay, so, and we have certain values of it. We don't know what the function rule is, but we know that the values of the function at certain points, and we also know the derivative at certain points. Okay, so the directions are to approximate f of 3.1. Okay, so we're going to approximate using the tangent line. Okay, so at 3, which is close to 3.1, we're going to find the y value at 3. We're going to find the derivative, the slope of the tangent line at 3, and we're going to use that to write the equation of the tangent at 3, and then we're going to substitute 3.1 into that tangent line. Okay, it's not going to give us the exact value of this function, but it will be close. Okay, so let's go ahead and get started. So here is where 3 is, right, where x equals 3. F of 3 is 24. F prime of 3 is 27. So the equation of the tangent line when x is 3 is y minus 24 equals 27 times x minus 3. And I can write that with y isolated, y equals 27 times x minus 3 plus 24. Okay, and now what I'm going to do is I'm going to take the 3.1 and substitute it into the tangent line to approximate what the actual value of the function is. Okay, so let's go ahead and do that. So y equals 27, 3.1 minus 3 plus 24. and we will drop it into our calculator. So we've got 27 times 3.1 minus 3, sorry about the lighting there, 3.1 minus 3 plus 24, okay? And that gives us 26.7. So f of 3.1 is approximately 26.7. Okay, so the actual value of the function here, or sorry, not the actual value of the function, but the actual function, surprise, what this actually is and what the derivative is taking the derivative of, it's actually x cubed minus 3. I just picked numbers from that function. So this is, all these values are x cubed minus 3. So let's just go ahead and see how close we are. So let's take the actual value just for fun. So 3.1 cubed minus 3 is 26.791. So the actual value of the function is actually 26.791. So it's pretty close, right? It's not precise, but it's close, right? And so back in olden times, they used to use this a lot because they didn't have the technology to be able to go back and do this. So people would often use the tangent line as an approximation when they couldn't have the original value of the function. So let me go ahead and encourage you, using that example now, to try this next example. So similar process, just different numbers. I want you to try to approximate f of 2.9 given this, this function that's continuous and differentiable in the interval that's shown. All right, so go ahead and give that a whirl. Okay, so hopefully you've had a chance to do it and we can check our work here. Okay, so what's close to 2.9 is 3. So we follow that same process that we did here for 3 because that's pretty close to 2.9. And then once we have our tangent line, we can substitute 2.9 in for x and approximate a value. Okay, so the value we would get would be 16.8. And then what this function actually is 2x squared. So if we actually did substitute 2.9 in for the real function of 2x squared, what will we get? So 2.9 squared times 2 would be 16.82. So again, it's pretty close. Okay. Okay, another thing about local linearity and local linearization and using this process that you have to kind of think about is whether you have an overestimate or an underestimate. So that is, you can look in your graph and see if you have a graph, you can look at the graph. So this is the graph from our warm-up at, right, looking at like the zooming in on the tangent line. And you can see that the tangent line at x equals 1, that blue line that we looked at in the warm-up, is actually above the graph, right? It's higher than the graph. So when we use the tangent line, it's actually going to be an overestimate, okay? Because that blue line is above the graph, okay? By contrast, if you have a graph that looks like this graph here on the right, it's going to be an underestimate because the blue line is below the graph. Okay, so how do you know when it's an underestimate or an overestimate? So if your graph is concave down, that means that you're going to have an overestimate, right? You see all these tangent lines on this concave down example are above the graph everywhere except the point where they touch the graph, okay? If your graph is concave up, which means the slope is increasing, you have an underestimate, okay? So concave down just means as you move to the right along the graph, your slope is decreasing, It's not that the graph is decreasing, the slope is decreasing. And then with concave up, your slope is increasing. If you're just looking at the shape of a graph, one way that I like to think about this is that a concave up shape, if you continued the shape and you poured like some milk into it, it would hold the milk. Concave down, if you poured milk on it, the milk would slide off. So that's, in my brain, the way that my brain works, that's like a helpful way to think about it. So the next thing I had you all do in class is matching pairs, concave up, concave down. So basically just testing if you understand what it looks like to be concave down and concave up. All right, so the next thing is, what if you don't have a graph? What if you don't have any information about what the graph looks like? You can determine concavity with no graph by looking at the second derivative, and that's where our calculus comes in. If your second derivative, f double prime of x, is positive, your graph is concave up at that point. If it's negative, your graph is concave down, okay? So that's just a way that you can determine it with no graph. So if you're doing this local linearization process, concave up, right? When you have that underestimate, if your second derivative is positive, you're going to have an underestimate. If your second derivative is negative, you're going to have an overestimate. Okay, so the last example here, and this is just bringing everything together, is giving you a function saying it's concave down at a certain point. What is the estimate for the value of the function? I don't know why we picked 3 because it's not really that close to pi over 2, but using local linear approximation at pi over 2. Is it an overestimate or an underestimate? So I wrote the steps down here. First, find f of pi over 2, find the derivative and f, that should say f prime, of pi over 2, and then using the information from steps 1 and 2, write the equation of the tangent line at x equals pi over 2. And then substitute 3 in for x in the tangent line and find y, just like we did in the table problems. And then lastly, use that second derivative to determine whether it's an overestimate or an underestimate. So go ahead and pause the video, give it a try. I'll give you some time to pause and try this problem. Go ahead and pause the video, try the problem. Have you paused the video yet? Go ahead and pause it. Pause it and try the problem. Thank you. Okay. Big reveal. So we find the actual value of the function at pi over 2, and we find that it is 1. Okay. We find the derivative of function, -2 sine x. We substitute pi over 2, and we find that the slope of the function at that point, pi over 2, is -2. So therefore, the equation of the tangent line is y minus 1 equals -2 x minus pi over 2. So if we take our approximation of f of 3, we just plug 3 in for x. Again, 3 is not that close to pi over 2, so I don't know why we did it this way, but like, you know, we're just practicing the process here. And then lastly, is it an overestimate or an underestimate? Because it's concave down, right? Concave down, it's going to be an overestimate because the tangent line is going to be above the graph at every point except that exact tangent, except that exact x equals pi over 2 point, okay? And I highlighted the green concave down, because that's what's going to tell you that it's an overestimate or an underestimate. Okay. So there's a homework on that in the module that you can practice. The second part of the lesson is L'Hopital, or depending on how you spell it, L'Hopital's rule. Sometimes you'll see it spelled like this with a little circumflex accent over the O. Apparently, originally, he spelled it like hospital back in hundreds of years ago when he lived. But you pronounce it L'Hopital. Okay. Okay, so here's the deal. Remember back in September when we were evaluating limits, right? The first thing we always tried was to do direct substitution, okay? Sometimes direct substitution would give us a zero denominator or an indeterminate limit, okay? And then we would factor, okay, which is totally fine. Sometimes though, you'll have a indeterminate limit, so it'll be 0 over 0 or infinity over infinity. And when that's the case, you're allowed to use what's called L'Hopital's rule, which is basically saying that if the limit of the ratio of functions is 0 over 0 or infinity over infinity, then the limit would be the limit as x still approaches that same point, that same x value, but of the ratio of the derivatives of the numerator and the denominator, okay? So I'm gonna take this example that we have here, and you can write it down with me if you would like. We have limit as x approaches 2 of x squared minus 7x plus 10 divided by x minus 2, okay? And what I'm gonna do is I'm gonna do it both ways. I'm gonna do it by factoring, and I'm gonna use L'Hopital's rule so you can kind of see the connection. Okay, so here we go. Camera, okay, so here is the ratio of functions. So if you actually substituted 2 in, right, 2 squared minus 7 times 2 plus 10 over 2 minus 2, you'd get 4 minus 14 plus 10, that's 0 over 0, okay? So this is indeterminate. So now you know that you can use L'Hopital's rule, but I also want to show you how you can also use what we did in September, which is factoring, okay? So let's just kind of leave this off to the side in a little cloud. So if you factor the numerator, you can see that it'll factor into x minus 5 times x minus 2 over x minus 2, right? And then you can divide out the x minus 2, substitute 2 in, because you have, what do you have remaining? X minus 5, right? So 2 minus 5 is negative 3, right? So that's how you already learned how to do limits, by factoring, canceling, and then substituting once you had something that wouldn't give you a 0 denominator, okay? But now let's try using L'Hopital, right? So since substitution gives an indeterminate limit, 0 over 0, right? We can use this rule. You can spell it hospital, or you can, oh, I can't even spell it. We can use L'Hopital's rule. So let's take the derivative of the numerator and then the derivative of the denominator, right? So basically the derivative of the numerator, we're gonna still have x, limit as x approaches 2. The derivative of the numerator would be 2x minus 7, right? The derivative of the denominator would just be 1, okay? So let's substitute 2 in and see what happens. So 2 times negative 2, sorry, 2 times, I don't know why I just said negative. So 2 times 2 minus 7 over 1. That's going to be 4 minus 7 over 1, which is negative 3 over 1, which is negative 3. So you see how that works? So we can, this particular problem we can do by factoring, but L'Hopital's rule is also going to work for us, right? Ratio of the derivatives. When you have an indeterminate limit, 0 over 0, infinity over infinity, you can take the derivative of the numerator, derivative of the denominator, substitute the x value in, and that will be your derivative at that point, okay? So feel free to pause the video here if you need to take anything down or process anything. Okay, and just to kind of close this all out, we did a practice problem in class using L'Hopital's rule for this, right? When you substitute 2 in, you get a 0 numerator and a 0 denominator, okay? So we can get, we can use L'Hopital's rule to, well, you should probably try to pause this and pause the video and do this problem before. So go ahead and pause it. And now we'll go over it, right? Because substitution gives 0 over 0, the limit as x approaches negative 2 is 1, right? That's the derivative of the numerator over the derivative of the denominator, and then we substitute 2 and we get 1 over 13 as our limit, okay? These are some practice problems. You can pause this video and try them if you would like to. And then just a reminder, L'Hopital is not the quotient rule. rule. Okay, so you can't just use L'Hopital's rule every time you see a ratio of two functions. It only works when you're trying to find the limit at a certain point, a certain x value, and the limit at that x value is indeterminate, 0 over 0 or infinity over infinity. Okay, so just make sure that you are clear. Like if you're just taking the derivative of a function that is a ratio of two expressions and you need to use the quotient rule, use the quotient rule. Okay, so don't get that confused. And then, like I said at the beginning of the video, the homework 4.6 and 4.7 are in the module along with the answer keys, so you can check your work. And then don't forget about your formatives for Monday and your multiple choice Wednesday assignment. Don't forget to do that by next Wednesday. Okay. Some helpful AP daily videos. I don't know why that log expression is in there. Some helpful AP daily videos that you all can watch are 4.6 and 4.7. So definitely avail yourself of those. They're very good. And thank you so much for watching, and I'll see you next time.